In this video, we're going to focus on Graham's law of effusion. We're going to talk about the equation, the concepts behind it, and also work on a few practice problems. So let's go ahead and let's begin. Let's get started. Number one, the rate of effusion of argon was measured to be 0.218 moles per second at a certain temperature. Calculate the rate of effusion for helium gas. Now, according to Graham's law of effusion, the rate of effusion is inversely related to the square root of the molar mass of a gas. So what this means is that as the molar mass of a gas increases, the rate of effusion decreases. Now this makes sense. So what this means is that heavy gas molecules move slower and lighter gas molecules move faster. So what exactly is effusion? Effusion has to do with how fast a gas can escape from a hole, or how fast it passes through a hole. So let's draw a box. So in this box, we're going to have a gas inside. And there's going to be a hole in the box. So let's say there's nitrogen gas inside. The rate at which nitrogen gas leaves this hole, or leaves the box through this hole, that's the rate of effusion. It's how fast a gas can escape from a container through a hole. It's similar to diffusion. Diffusion is basically the movement of material from a region of high concentration to a region of low concentration. But the difference between effusion and diffusion is effusion is related to a gas escaping through a hole from a container. And that's the main idea behind it. Now the equation that you need, Graham's law of effusion, it's R2 over R1 is equal to the square root of the second molar mass divided by the first one. Actually, it's the other way around. It's M1 over M2 because they have to be inversely related. So now how can we use this formula to calculate the rate of effusion for helium gas? Well, first, let's find the molar mass of argon and helium gas using the periodic table. So for argon, the molar mass is about 40 grams per mole. It's 39.95, but I'm going to round it to 40. And for helium, it's about 4. So we want to find the rate of effusion for helium. So I want helium to represent subscript 2. The reason being is it's going to be easier to solve for R2 instead of R1. If you try to solve for R1, you're going to have to flip the fraction, but I'm going to prefer to solve for R2. So helium is going to correspond to subscript 2, and argon is going to correspond to subscript 1. So the rate of effusion for helium divided by the rate of effusion for argon is therefore equal to the square root of the molar mass for argon divided by the molar mass for helium. So let's make some space. And now let's plug in the information that we have. So the rate of effusion for argon is 0.218, and the molar mass for argon is 40, and the molar mass for helium is 4. 40 divided by 4 is 10, and the square root of 10 is about 3.162. So to solve for the rate of effusion for helium, let's multiply both sides by, let's cross multiply. So this is going to be R times 1 is just R, and 0.218 times 3.162, that's about 0.6894. So that's the rate of effusion for helium. That's how you can calculate it. So notice that argon is a heavier gas, and so therefore the rate of effusion for argon is less than that of helium. Heavy gas molecules move slower, and helium is lighter than argon, and so it has a much higher rate of effusion. Lighter gas molecules move faster. Number 2, An unknown gas has a rate of diffusion that is 4 times faster than oxygen gas, O2. Determine the identity of this gas. Whenever you want to identify the identity of a gas, especially in a multiple choice problem, you need to calculate the molar mass. And then once you have it, you can see which molar mass matches with the choices that are listed below. So let's begin. Let's start with the equation for Graham's law of diffusion. And now, we need to know which substance is going to correspond with which subscript. So, we need to find the molar mass of the unknown gas. So, it's easier to solve for M1 rather than M2 because M1 is on top. So 1 is going to correspond to the unknown gas, and 2 is for oxygen. So what we have now is R of O2 divided by R of the unknown gas. That's going to equal the square root of the molar mass of the unknown gas divided by the molar mass of O2. So let's plug in the information that we now have. So let's look at the first sentence. The unknown gas has a rate of diffusion that is 4 times faster than oxygen gas. So if the rate for oxygen gas is 1, that means the rate of diffusion of the unknown gas is 4 times as great. So it's going to be 4. If the rate of diffusion for oxygen was 2, then for the unknown gas it has to be 4 times as great. It's going to be 8. So 4 to 1 and 8 to 2 is the same. So it doesn't matter which numbers you use. As long as the ratio is 1 to 4, you're going to get the answer right. So we're going to plug in 1 for O2 and 4 for the rate of diffusion for R of X. Now we don't know the molar mass for substance X, but we do know the molar mass for O2. For oxygen, it's 16, so 16 times 2 is 32. So let's square both sides of the equation. So 1 squared is 1, and 4 squared is 16. And on the right side, when you take the square of the square root, the square and the square root cancel. So it's simply going to be m over 32. So now let's make some space. So now let's go ahead and cross multiply. So 16 times n is simply 16m, and 1 times 32, well, that's 32. And if we divide both sides by 16, 32 divided by 16 is 2, so the molar mass is 2. Therefore, the answer has to be A. Hydrogen has a molar mass of 1, so H2 has a molar mass of 2. Helium has a molar mass of 4. For nitrogen gas, it's 28, 14 times 2. For CO2, it's 12 plus 16 times 2, that's 44. And for CO, it's 12 and 16, which is 28. So only hydrogen has the same molar mass as what we just calculated. And that's how you can determine the identity of the gas if it's a multiple choice problem. Number 3. It takes 3.12 seconds for a sample of krypton to diffuse from one compartment into another at a certain temperature. Determine the time it takes for an equivalent sample of neon to do the same job. So now let's review Graham's law of diffusion. As the molar mass of a gas increases, we know that the rate of diffusion decreases. Heavy gases move slower, lighter gases move faster. Now, if the rate of diffusion decreases, what about the time? Even though heavy gases move slower, they take a longer time to get the job done. Lighter gases, which move faster, they take a shorter time to get the job done. So let's say if you're driving from, let's say, Chicago to New York. If you're driving at 70 miles an hour, you're going to get there relatively quick, relatively fast, so to speak. But if you're driving at 30 miles per hour, you're going to take a long time to get there. So, as the rate of diffusion decreases, the time it takes to get the job done increases. Make sense? Now, notice that molar mass and the rate of diffusion are inversely related. So that's why we have the equation R2 over R1 equals the square root of m1 over m2. Here, the 2 is on top, but here the 1 is on top. It's because it's due to the inverse relationship between the molar mass and the rate of diffusion. But notice that the molar mass is directly proportional to the square root of the time. So therefore, this is going to be equal to T1 over T2, because as the molar mass goes up, the time it takes for it to travel from one compartment to another is going to go up as well. And so that's why the subscript 1 are both on top. So now let's go ahead and solve this problem, now that we have the equation that we need. So we're looking for the time it takes for neon to do the same job. So neon is going to be T1, and for T2, we're going to use krypton. So this is going to be equal to the square root of molar mass 1, which T1 is neon, so molar mass 1 has to be for neon. So M for neon, and divided by the molar mass of krypton. So right now we need to refer to the periodic table. So the time it takes for krypton to effuse from one compartment to another is 3.12 seconds. And we're looking for X, which is the time it takes for neon to get the job done. Now the molar mass of neon, according to the periodic table, it's about 20.18. And for krypton, it's 83.8. So first, let's divide 20.18 by 83.8, and you should get 0.2408. And now let's take the square root of that number. So you should get 0.4907. So X divided by 3.12 is equal to 0.4907 over 1. And let's go ahead and cross multiply. So 1 times X is X, and 0.4907 times 3.12 is 1.531. So this is the time it takes for neon to do the same job. Now it makes sense though. The heavy gas molecule, which is krypton, or it's really an atom, it takes a long time to get the job done because it moves slower. It takes 3.12 seconds to effuse from one compartment to another. Whereas neon, which is lighter, it moves faster, so it takes a shorter time to get a job done. So that's basically it. That's how you can calculate the time it takes for neon to do the same job as krypton. So by the way, if you want more practice problems on general chemistry, if you're taking the General Chemistry 1 final exam soon, or if you're taking AP Chem, check out my video. It's entitled AP, IB, and College General Chemistry 1 Study Guide Review. You can check it out on YouTube, and you can find plenty of multiple choice problems on gas laws, stoichiometry, solution stoichiometry, calorimetry, enthalpy, things like that. Basically, most of the topics that you need to cover for your first semester of college general chemistry, or if you're taking AP Chem, it's going to cover the first half of AP Chemistry. So thanks for watching, and have a great day.